Okay, welcome everyone to yet another tutorial on how to run biomechanical implant evaluations using SolidWorks, Mimics, and Abaqus. In this video, similarly to the positioning a humeral implant in a Mimics bone model video, we're going to be essentially doing a step-by-step instruction guide on how to bring a SolidWorks-positioned implant into Abaqus, how to apply material properties using Mimics, and then bring those material applied models back into Abaqus for analysis. For most of you, I'm sure that the most interesting portion of this video will be the step-by-step instruction guide on how to apply the basic settings required for biomechanical analysis in Abaqus. As we get started here, you'll be able to see me create an initial analysis file. This will be predominantly used for creation of an Orphan mesh, as well as implant positioning and the resection of the full bone models. To start off, just import your step files for your bone models as well as your cut tools. It's important that you use discrete geometry cut tools in Abaqus directly as opposed to performing your resections in SolidWorks, as those resections become much more compatible with the software. It is of course possible to perform these resections in SolidWorks itself, but it's highly not suggested. As you may have noticed, some of the parts that I'm importing here contain imprecise geometry. This is important if your imprecise geometry is within the area of interest that you're looking at. However, in this case, I'll be resecting off those areas immediately. After importing your bone and cut tools, feel free to import your prosthetic model. It's important that your prosthetic model, though, is fully airtight and has no voids internally. This will be discussed in a future video, and much troubleshooting can be saved if you take a little bit more time ensuring that you have a proper prosthetic model prior to import. Another good practice is to ensure that you do a geometry diagnostic query to ensure that your part contains no invalid entities. We'll be able to deal with imprecise entities, but invalid entities will be much more of a headache than it's worth. So I would probably suggest that instead of importing invalid entities, you go back to your design and you ensure that you have a fully enclosed, watertight volume or solid body without any imprecisions. As we begin our in-silico resection procedure, ensure that all your cut tools are properly positioned. Under the assembly module, cut your geometry and suppress the original instances. If you're planning on breaking up trabecular and cortical bone, I would probably suggest that you start off with a full bone model and a trabecular bone model. By subtracting the trabecular bone model from your cortical bone model using a Boolean subtraction, you'll be able to achieve a thin cortical shell without worrying about any kind of work in Mimics, as the reducing and wrapping features of Mimics are sometimes a little bit difficult to work with. After you've isolated your trabecular and cortical bone models, ensure that they're cut with your implant, and also double check to make sure that you create a cortical and trabecular set, as this will be very important in the future. Also, make sure that you're saving very frequently, as Abaqus is not very forgiving when it comes to undoing actions. After you've completed all your resections, now it's time to create a total bone model. This can be done under the assembly module, where you merge your geometry but ensure that you suppress your original instances and retain your intersection boundaries. Now that you've created your merged, resected, and finalized bone model, it's time to apply global seeds. Here you can see I'm using a global seed size of 1.2 millimeters with curvature control of 0.05 and minimum size control of 0.01. These values are very specific to my analysis, so ensure that you do the proper research in order to understand what settings are required for yours. For my finite element analysis, I would like to use solid tetrahedral elements. So here you can see me assigning C3D10 quadratic tetrahedral elements to my model. Sometimes this process can be a little finicky. If you run into issues, the first thing you should do is assign your mesh controls as well as your element type, then reseed your part, and most errors should go away. Before progressing, please query your mesh and just validate that you have a good mesh. After this step, you're kind of stuck with the mesh that you have, so please ensure it's mesh that you want before continuing. The next step in our analysis is to create a job and write your input file to your working directory. This process will allow us to create an orphan mesh, which we will then use for our material property assignment. After creating your orphan mesh, from the Model menu, open up your orphan mesh and re-import your .inp file as another model. Your new model file will contain your total bone mesh that you produced in the last step. Copy this part twice and rename your two new parts as Cort and Trab, or some similar naming convention. Now this is why it's very important that you create the sets in the first step, because as we work here, we're going to use those sets to delete the associated elements and discretize back into our trabecular and cortical meshes separately. This can be done by deleting all of the associated trabecular elements from your cortical model and vice versa. After you've recreated cortical and trabecular meshes, go back and suppress your cortical model to create a trabecular input file, and vice versa. These current existing mesh files will then be able to be uploaded to Mimics for material application. Now that we've created meshes for both our cortical and trabecular bone, open up Mimics and the associated patient file. Import your cortical model, and we'll apply that material property first. Once your cortical model has been successfully imported, open up the Material Application screen. Here we're going to apply homogeneous material properties with a Young's modulus of a static 20,000 megapascals and a Poisson ratio of 0.3. After that nice warm-up for material application, we're going to do the more complex trabecular material application process. To get started, import your trabecular mesh and open up the same material property application screen as you did with the cortical. Here, we're going to use our CT phantoms to identify what Hounsfield unit is associated with what calibrated density. For our lab, we use a SB3 cortical bone block and a bottle of water for this purpose. Right here, I'm thresholding a line using the Draw Threshold Line tool in Mimics to identify what average density is associated with the Hounsfield units of the cortical bone block. Here, I'm merely repeating the same process, but this time while using the water phantom. Once you've identified your Hounsfield threshold units, we're going to create a gray value based material with a 20 number of materials. Here you can see that I'm identifying the -24 Hounsfield unit as a density of 1 gram per centimeter cubed. Thanks to my thresholding line, I've identified a Hounsfield unit of 1426 as my density of 1.82 grams per centimeter cubed. Here you can see me using the Morgan et al. Relationship for Young's modulus to density and applying a static Poisson coefficient of 0.3. Prior to proceeding, just make sure you do a logic check for your assigned Young's moduli. Here I've seen that my assigned Young's moduli from my relationship exceeded 20,000 megapascals. As I know from the literature, it's rare that trabecular bone Young's modulus would exceed 20,000 megapascals, so I'm just setting a manual limit here. Now, go ahead and export those new material applied model files. To get started setting up our analysis, import your recently exported material applied model files into Abaqus. This can be done by right-clicking on the models portion of your models tree. Please ensure that after importing your cortical homogeneous bone model that you rename the part, the section, as well as the material. If you neglect to do so, then your cortical will be overwritten by your material, your part, and your sections for your trabecular bone upon import. Separately import your material applied trabecular model, and it should show up as a new model. Here I've just found that it's easiest to rename your new cortical model as your working analysis model. You can now copy over all parts, materials, and sections from your trabecular bone model. With our bone models imported, we should now be able to merge them and get started with our analysis. Under the Assembly module, we can now use the Merge Cut Instances tool to merge our trabecular and cortical bone instances. When using the Merge/Cut Instances tool under the Assembly module, ensure that you are merging both your mesh and geometry while suppressing original instances, retaining your intersection boundaries, and reset your mesh merge nodes property to boundary only with a tolerance of 1 micrometer. Here, I like to copy over my original implant part from my resection procedure, but if you're analyzing press fit or if it's easier for you, then bringing in a new implant step 214 file is also acceptable. Now that we have a full material applied bone model ready to go, we can start setting up our analysis. Begin by assigning property and sections to your new implant. Here, I'm assigning titanium properties and Young's modulus of 110,000 megapascals and Poisson ratio of 0.3. Moving forward, we can begin in the step module, creating a new step relevant to our analysis. Here, I'm assigning a step with nonlinear effects active and using the iterative solver because I have more than 1 million degrees of freedom contained within my model. This next part is very specific to my own analysis. One of the outcome variables of my own study is risk of stress shielding at the proximal calcar region of the humerus. I want to request a targeted field output variable at this location, so first I need to use the section view and display group tools to create a 2mm by 10mm element set at that region of the humerus model. Once you've completed all the pre-work required for your field output variables, it's time to assign what output you'd like to see from Abaqus. Remember that the more targeted your field output variables can be, the less memory and computational power your analysis will take. This can be extremely important as the output database files for one of these analyses will be upwards of 5 gigs. Once you've completed your step settings, we can move on to our interaction properties module. This can be very specific to your own analysis, but as an example, I'll show myself assigning 2 different contact interactions for different spots across my implant. Begin by assigning surfaces to all of the relevant geometries of your implant. Next, assign surfaces to the mating counterparts on the bone model. Now that we have our surfaces created, we can begin by assigning interaction properties through the Interaction Manager. Here, I'm assigning a finite sliding surface-to-surface interaction to my implant. I'm adjusting to remove overclosure and creating a new interaction property with penalty tangential behavior and hard contact normal behavior. We've now finished up with our surface-to-surface interactions, so I can continue on to distribute my load across my surrogate implant surface. For my implant, I want to apply load at the center of rotation of my implant, which is shown by the peak of the cone on my implant model. In order to apply this without causing a stress concentration, I need to create a constraint through the creation of a reference point, and applying the force from that reference point to the rest of my cone surface. As one would expect, the forces applied to your implant will be dependent on your own study. Here, I've used MATLAB to transform instrumented implant data into the vector space of my local CT humeral coordinate system. It's important that you apply this force directly to the reference point, which is now part of the implant geometry. For my boundary conditions, I am applying Ancaster boundary conditions to the distal resection surface of my cortical humerus. This, again, should be unique to your own analysis, and there should be some sort of data indicating what boundary condition is considered far field from your areas of interest, and will therefore not affect your primary outcomes. Here, I'm just meshing my implant model with the same settings that I used for my bone model. You may want to apply mesh controls to your own model dependent on the requirements of your own analysis. We should now be ready to run analysis. Create a new job to perform a data check to ensure that your models are acceptable. As you can see here, my analysis was aborted due to 6 elements having a volume of 0 or negative. I can troubleshoot this by going to my output database and then listing through querying which elements have a volume of 0, and then going back into my model, creating a display group for those elements, and then deleting them in the mesh module. I know this was a long video from start to finish, but you made it through. You're now ready to run your first analysis on the biomechanics of an implant model in silico. If you want to learn how to position your implant or how to create bone models from CTs and mimics, then please take a look at my YouTube channel and you'll find similar guides on how to do those things too.